Section 4.2, logarithmic functions and their applications. In 4.1 we covered exponential functions and their applications. So today we introduce a new kind of functions called logarithmic functions and their applications. And we're going to see the relation between logarithmic functions and exponential functions. So to start with this, we start by introducing the definition of logarithmic functions. What are logarithmic functions? If we have y is written as log of x base a, that's how we read it. Y equals log of x base a. Or you can read it y equals log base a of x. So either one is fine. This is defined or equivalent to say a to the y equals x. So watch how I go with this. This a, the base, to the y equals x. A to the y equals x. So this part on the left side, this is the logarithmic form. I call it log form. This is the exponential form. Exponential form. Here a is bigger than 0 and it can be 1. Just keep that in mind. It's important. So how do we apply this definition? So let's say someone asks us to find the value of log of 27 base 3. How are we going to find this? Well, to start with this, I'm going to let this be m or u or any letter you like. Now my goal is to find the value of that letter u. Okay, so how do I find the value of that letter? I use the definition. It says the base 3 to u equals 27. So 3 to the u is 27. And in the previous section, we learned how to solve such kind of equations. And the first thing we need to do is prime factorize the 27 as 3 to the third power. Now they have the same base. We can set the exponents, u and 3 equal to each other. And that's what I'm looking for. So this tells me that log of 27 base 3 is exactly 3. Another example. Let's say we're asked to find log of 1/8 base 2. So same procedure. We let u equals this. Then we rewrite it using the definition of logs. 2 to the u equals 1/8. But 8, you prime factorize it as 2 to the third power. Then you can rewrite this, bring it up as -3. So then u equals -3, and that's what the answer to that given expression is. More practice. Let's say find the value of log of 4, but I'm going to make the base 1/2. So same procedure. So what are we going to do here? We are going to let u equals log of 4 base 1/2. So then get 1/2 to the u power is 4. How are we going to solve this? The first thing I can do with 4 is make it 2 square if you prime factorize it. So to match the bases, I need to bring this 2 up, which I'm allowed to do so by rewriting as u to the -1. Keep the right hand side the same. Then multiply these using the properties of exponents and keep the right hand side the same. Now the bases are the same, so you set the exponents equal to each other. So then u equals -2. That's just kind of like practice, so you memorize the definition. Be familiar with the definition of logs. One thing to note, as you could see the bases, sometimes you might come across a function that says log x, just log x, no base. Doesn't mean someone forgot what the base is. This automatically means base 10. So everything we work with is, if it's not specified, automatically means base 10. Just keep this note in mind. Now I'm going to take a specific example, log x base 2. And I'm gonna find the inverse of this. If you remember from previous chapters, we learned how to find the inverse of a function like this. And how do you find the inverse? There's two steps. We switch x and y, just to recall that, and then solve for y. So how do we switch x and y? So this makes it x equals log of y base 2. Now I need to solve for y. To solve for y, we need to find a way to get to that log thing, log. So we can use the definition. The base 2 to the x equals y. So if the function, the given function, call it f of x, then its inverse is 2 to the x. So that tells me that the inverse of the log is the exponential. Inverse of log is exponential. So why does that matter? Well, let's see. What about if someone asks you sketch a graph for a function like this, y equals log x base 2. Well, I don't know how to do this by hand for now, right? And I can't use any technology to graph such a function. So what I'm going to do here, is I'm going to use its inverse. So the inverse, which is y equals 2 to the x, I'm going to create a table of values for this function, as we did in the previous section. We took 0, 1, 2, negative 1, negative 2. So 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4. Why did I find the values or the table of values for the inverse? Well, because now I can reverse everything. Remember, in the inverse, x and y get switched. So now when I'm talking about this function, watch what I'm going to do. I'm going to take these values that I just obtained and switch x and y. So 1/4 comes here, negative 2 goes down. 1/2 comes there, negative 1 down. 1, 0, 2, 1, 4, 2. So now that gives me the table of values for the main function, y equals log x base 2. And that would really help me now to graph the function. Okay, so I'm going to sketch the graph for the function. Y equals log x base 2. So let's see what we have here. 1, 0, that's the first point I'm going to plot on the graph. 2, 1, 2 and up 1. 4, 2, so 3, 4, and then 1, 2. And then we have 1/2 somewhere here, negative 1. And then the next one is here. So it's approaching the y-axis, as you can see. It's approaching the y-axis. So label everything. Plot the points, label the 1, label everything, the x-axis, y-axis, origin, put the arrows at the end or at the tip of the curve. And this is the graph of y equals log x base 2. I'm going to show you something here. I'm going to graph also sketch the graph of the 2 to the x. 0, 1. 0, 1 it was here. 1, 2. So 1, comma 2. 2, comma 4 up there. And then negative 1, 1/2. So I'm using the first table. And we graphed the same one earlier in the previous chapter. So I graphed these, and I'm going to graph one more piece of information. Y equals x. So we know from previous chapters, so this is the graph of y equals 2 to the x. From previous chapter, that the function and its inverse always are symmetric with respect to y equals x. What does that mean? That means if we fold the paper on the green line, the y equals x, the two graphs should coincide with each other, should be exactly the same. So the y equals x is like a mirror. Notice here in the y equals x, this line, we called it y equals 0, was a horizontal asymptote. Horizontal asymptote. In the inverse, that horizontal asymptote becomes x equals 0 for the inverse, which is the vertical asymptote, or vice versa. So you can have the exponential original and that's the inverse, or vice versa. So how did that change? Like, why that happened? Remember, when we do find or work with inverses, we switch x and y. So I expected the horizontal to become vertical, like y equals 0, x equals 0. What other information we can get about this function as analysis? Well, I always like to find the domain of that function. It's from 0 to infinity. The range is all real numbers, negative infinity to infinity. It's a one-to-one function, so I'm gonna put these as points. So it's a one-to-one because it passes the horizontal line test. A one-to-one function. It's an increasing function over its domain. What other information good to learn here? We said x equals 0 is the vertical asymptote. And the intercept, there's x-intercept at 0, 1, 0. Now, that's good for the graphing. Now, what about describing transformations? Describe transformation to sketch a graph for each function below. So we don't have to graph them, but just to say how to use transformations using the graph of y equals log x base 2. So we're gonna try to find or use transformations. So the first one is y equals log of x minus 1 base 2. The second one we're gonna work with is log of x plus 2 base 2. So what's the relation between these? Well, originally was log x, now I see x minus 1. So a change was made on x. If a change is made on x, we always set that change equal to 0. And then add 1 to both sides. I get a plus 1. So remember, change on x means either to the right or to the left. That's what change on x, right or left. Well, in this case, x is a plus. So this tells us we need to get the graph of this. We shift the graph of the original function, which is y equals log x base 2, 1 unit to the right side. 1 unit to the right side. For the next one is a similar question, change on x. So we set x plus 2 equal to 0. I got x equals negative 2. So this means shift 2 units to the left. This means shift the graph of log x base 2 2 units to the left. What about they make more changes, like different function? Y equals negative log of x base 2 plus 3. So I see two changes here. Two changes. The first change is the negative sign. So the first thing we do, the negative sign, always y, make it negative y, means reflect the graph of y equals log x base 2 about the x-axis, as we've seen in the previous section. And the plus 3 means 3 units up. So we shift the graph of log x 3 units up. What about when we need to find the equation of the inverse for a function like this? 1/3 times 2 to the x minus 4. The first question, people say, wait, but this is not log. Why am I doing exponential here? That was on the previous section. Well, let's see what happens. This means y equals, so it's y equals 1/3 times 2 to the x minus 4. To find the equation of the inverse, two things need to be done. First, switch x and y, so make x y, y x, as you see. And now we need to solve for y. So here we switch x and y. And now we need to solve for y. How do you solve for y? First thing that bothers us here is the 1/3. So if you multiply both sides by 3, that makes it 3x equals 2 to the y minus 4. And how am I going to solve for y here? See, the bases don't match, so I can't set the exponents equal to each other. But what we can do, we can go backwards with the definition. So what that means, remember, if I put a log here, the base 2, see this is base here is considered. That base goes in the denominator down there. And remember, based on the definition of log, 2 to some power, so 2 to the y minus 4, so 2 to the y minus 4 equals 3x, so 3x goes here. That's backwards of the main definition that we started this section with. 2 to that thing equals 3x. So now remember, I'm solving for y. So all I have to do, add 4 to both sides, and that gives me the equation of the inverse. So this is the inverse of the function they ask us to find. We can look at another example similar to this. Find the equation of the inverse if f of x is 5 to the x plus 1. So what do we need to do here? We need to switch x and y. So this is y equals 5 to the x plus 1. Make y x, x, y. So y plus 1. Now we need to rewrite this log something equals. So the 5 is in the base. 5 to y plus 1 equals x. Subtract 1 on both sides. And that gives us the inverse. That's the inverse. To apply the main definition of logs even more, let's apply it to solving equations. So solve each of the following equations. Let's say we're given log x base 3 equals negative 3. And we want to solve this, this equation. So how do we start solving this? The main definition said the base, this to this, equals this. So 3 to the negative 3 equals x. So that means I don't leave answers with negative exponents. So bring that thing down, 1 over 3 to the third, as you can see. Now, what we got here is x equals 1 over 27. Another example. Log x minus 2 base 2 equals 3. Well, same way. Same procedure. So what do? 2 to the third power equals x minus 2. So x minus 2 is 8. Add 2 to both sides. Next one. Negative 1 equals log of 2x base 3. 2x base 3. So all we have to do is use the definition of the derivative. That's the only tool I have in my hands here. 3 to the negative 1 equals 2x. Okay, so what am I going to do with this? We don't like to see negative exponents, so bring it down, becomes like so. And then as a next step, I'm going to rewrite this. Look, the easiest way to simplify this is multiply by 1/2. Don't divide by 2 because you're going to end up with a large, like ugly fractions, or called complex fractions. So then x is very simple to multiply here. You got 1/6. What about if we look at something, another equation that doesn't have a logs in it? Let's say something like this. Okay, so how do we start with something like this? I don't see logs in here. The first thing that makes this difficult is having a fraction at the beginning of the equation. So maybe if I bring this up, when you bring this up, it becomes negative, as you know from the properties of exponents. Now, to get x down, the only way to get x down is to use logs. So how do we use logs? We use the definition of log, as I said before. 7 is the base, so 7 is in the base, so 7 goes in the base here. To the negative x equals 3. But remember, I'm solving for x, so multiply by negative, both sides. So that gives me the x value. So that's good practice on solving logarithmic equations or equations involving logarithms. Now we have a special case. Let's recall this e that we introduced in the previous section, which is about 2.7, e for exponential. So sometimes if you write log x base e, because e is a number, so you can have that number there and it's bigger than 0 and it's not 1. So it's okay to have log x base e. So mathematicians in the old days, they used logs base e a lot. So they decided to come up with a symbol to make it as a shortcut for them. So they said, let's call it ln of x. So this automatically means the base is e. The base is e. And this is called natural log. So you can read it ln of x or natural log of x. Natural log of x automatically means base e. So instead of writing log x base e every time, you can just simply write ln of x or natural log of x. So to practice on this and others, let's try to write each in exponential form. Write each in exponential form. Number 1, y equals log base 5 of x plus 1. Okay, that's the first one. So how do we write that down? We go 5 to the y power using the definition equals x plus 1. That's all you have to do. That's the exponential form. Let's apply ln or natural log of 5m. So how do we apply this here? We start by noting the base is e, that is hidden. E to the y equals 5m. Done, because that's the exponential form, no logs. Another example. What about ln of x plus 3 equals y? So it doesn't matter if ln on the right side or left side, the base still over there as hidden. So e to the y equals x plus 3. E to the y equals x plus 3. Now what about backwards? Can we go with backwards? So write using logarithms. Right, using logarithms. The first one, 5 to the x is 21. The next one we're gonna go over is this one, equals 16. So how do you write this using logarithms? We have been doing this today. So log, the base is 5. 5 to the x is 21. We don't have to solve for x, we're just rewriting it in log form. Same thing with this. When I see LE, that reminds me of ln. ln, the base is e, so it's like e to the x minus 2 is 16. But you don't need the e there. So next example, more examples. Say 5 equals e to the x over 2. And the fourth one, I'm going to go over 8 equals 3 to the x plus 11. So how do we write this out? Again, I'm going to use ln. So ln base e, e to the x over 2 equals 5. And then you can get rid of e. Number 4, it's there's no e here, so I'm going to use log. Log of something. So the base 3 goes really down in the base. So 3 to the x plus 11 is 8. Is 8. See, so that's how we convert from logs to exponential and vice versa. The idea behind this is to help us to solve equations. And why do we need to learn how to solve such equations? You will see when we get to the applications, you will see why we need this. Why we need this. Now let's look at a slightly different kind of solving equation here. Let's say 10 to the x. In the previous lesson, I remember we had like 100,000. And then we rewrote this as 10 to the 5th. So the bases match. But now what about if I don't want this? Let's say I'm going to pick a number that I can get it as 10 to some power. As 10 to some power. Let's say 20. So how do we solve for this? Well, log is the key because the only way to bring the variable down is using logs. So log, let's say 10 goes here and x there and 20 here. So that tells me, hey, x is simply log 20. Remember, when I say log 20, it means automatically base 10. So if you write 10 or not, it's the same. And then this, if you like to put this on the calculator, which I'll show in a different video, that will give out about 1.3, about 1.3. So keep that in mind. The next thing to introduce here, what about if I'm solving an equation but has two logs in it? So the bases, they match, log m equals log n, and the bases are a's. This equivalent to say m equals n. So this equation holds or true when m and n are the same because the bases match. So the m and n, they must match. And then how do we apply this? Let's say we're asked to solve log 4x base 2 equals log of x plus 6 base 2. Before I solve this equation, one thing we need to know about this is that if we look at the original graph, like the graph of log x base 2 when I graphed it, that graph, notice how it fell to the right of the x-axis. So this means log can take only negative, positive values. So if you try to plug in negative value for x in the logs, it's going to give us an error on the calculator. So only x values you can choose is from above 0. So only this part. You can't pick negative values. Because if you pick something in the negative, there's no value for y. There's no graph there for the log. So this tells us when we are solving equations in logs, we need to make sure whatever answer we get, that answer doesn't make that log negative. So it keeps it positive. So in this case, if I apply this property right above there, the bases are the same. So this means 4x must equal x plus 6. If you subtract x on both sides, you get 3x equals 6. Divide by 3, you get x equals 2. See, if you try to substitute this back in here and here, you got 8 and 8 for both of them. So it means this is an okay solution. It satisfies the equation that I just wrote. What about if you look at a different example? Solve log of 2x base 3 equals log of 24 minus x squared base 3. So now they have the same base. I can use the property that 2x equals 24 minus x squared. This is a quadratic equation. Always when we have quadratic equations, we move everything to one side, equal to 0. So if you add x squared to both sides, you get x squared here. If you subtract 24, and that will vanish, it will go away as 0. Let's see if this is factorable, as we did in the previous chapter. This is x. Two numbers apart, 24. Could be 12 and 2, no, or maybe 6 and 4. 6 and 4 works, so plus 6 minus 4. And you can test it out. Now, in order for this equation to equal to 0, x plus 6 must equal 0, or x minus 4 is 0. So subtracting 6, and here adding 4. Now let's see which one works. Does negative 6 work? If you substitute negative 6 here, that will give us a negative value, which is not going to work out. And both are going to be different. So the log negative, this negative doesn't work out. What about the 4? If you substitute the 4, you get 8. And the other side, you get 24 minus 16, which is also 8. So x equals 4 as well. So in general, just so you know, keep in mind, if we have a function written in the form log of f of x base a, then make sure that f of x must equal to 0 for all x. No matter what x is, this quantity that comes after log must be bigger than 0. It's so easy for students to miss on the test. Now, how do we apply this as an application? Let's look at this one. If $12,000 is invested at 6% compounded continuously, then how long will it take for the investment, means for the money, to grow to 15,000? So this is an example that tells us, hey, you don't have to wait and just keep watching how long it's gonna take. You can find it right away before even you deposit the money into your account, savings account or any other account. So if you remember from the previous section, we taught you, because this is compounded continuously, means we're gonna use this formula, PERT. That's the formula for compounded continuously. The initial amount that you always deposit in here, that's the principal, so that's the 12,000. E. R is the rate, which is 0.06. And the time, how long it's gonna take, is T, I don't know. So how long, so that's T, the time. To grow to 15,000. To grow to 15,000. So now, we are going to solve for T. How are we gonna solve for T? The first thing we do is we eliminate that E part. So by dividing by 12,000. And what we get, this is gone, the zeros cancel. And 15 over 3, 15 over 12, that's 1.25 equals E to the 0.06T. So now, how am I gonna do this? Remember, to bring the T down, the only way is to use logarithms. And since the base is E, that reminds me of using ln. So ln of something. So there's a base, E to that power equals 1.25. So you can get rid of E. Then I need T. You divide both sides by 0.06. So if you don't have a calculator or you're not allowed to use calculators, this is fine. You can box this as an answer. But if you decide to use the calculator, put that on the calculator, it will take 3.72 years for the money to grow from 12,000 to 15,000 at the given rate, compounded continuously. So that's an application how. So the main step is, it was from here to here, how we used logarithms to help us solve for T. That's why we learned how to solve equations involving logarithms. So that's why it's important that you are using an actual example from real life situation to show you how you can get the exact time that for your money to grow. So this way you can decide, should I put the money in or should I use it for a different investment? So this helps a lot for people to make decisions in real life situations. And that's what this section is really about.